All right. Hello, folks. Let's out of the way a little bit. Get these cameras perfectly situated. All right. Hello again. It's been actually the longest break I think we've taken from a book club, almost a month now. And also, jet lag is real. So if you see me being a little slow or tired, it's a big time shift from New Zealand here. But super glad to have all you folks back. I'm back in with my fairly complicated setup here, so let me know if anything doesn't look right or isn't working. I used the same camera actually to go take pictures, so I had to take it off of its streaming settings to bring it into normal camera settings. But I think I got everything back. So with that, today we are going to cover linear Gaussian state space models in Dynamax. These are a really cool class of model that have been used. My audio is cutting on and off a little. All right. That is something that's going to be tough to troubleshoot live, but we will. All right, it's something I'll have to do afterwards, so hopefully it's not too bad. Thanks, Chad, for letting me know. Well, today then we'll probably have a shorter session. I don't want to subject you to too much of an audio challenge, so let me jump straight into the material. Let's turn off the chat. So as always, I'm pulling everything out of from the Dynamax repo we have. Anyone doesn't know where that is, let me know. Hello, Theo. Hello, Charlie. Okay. Good to know everything's set up. Yeah, there's someday I'll take a picture and I'll show you, but there's a two microphones now. There is an audio box that goes through in a camera and restream. There's like 6 distinct pieces of physical and digital technology. Not even to count the physical computer, Linux computer I'm running, and man, what am I struggling? Yeah, well, actually, the physical computer and Linux. Those are the two things, because Linux had its own set of audio issues. Anyhow, it's the whole thing. But we're not here to talk about technology setup issues. We're here to talk about state space models. So I'm going to ask right here at the beginning, how many of you are familiar with linear Gaussian state space models, have either used it or read about it? The reason I ask is it's actually really, really interesting historically. I can talk about it. Let me turn this back on. I can talk about it more, but it's sort of the Kalman filter and linear Gaussian state space models are one of these models that have been around for a super long time. So and used for a super long time. So if we take our most interesting model as of late, which is a neural network, and specifically in its ChatGPT form, this is the first time a lot of people have seen or used a neural network that they know of, like ChatGPT. But Kalman filters have been around for almost as long, just same sort of era and time frame from what I understand. But they've been used extensively, right? Extensively in all sorts of physical applications. So there's a lot of literature on it. There's a lot of books on it. There's a lot of people that have been using this technology for years, albeit in a slightly, I don't want to say basic, but analytical form, which we'll talk about in a second. So to bring that all back around, that means a lot of you may have already studied the Kalman filter if you've taken dynamics classes and whatnot in the last 4 decades, but some of you may not, so I'm curious. See, Theo says, let me move back to my virtual window. Theo says he's familiar, haven't read the chapter to ProbML, but read and implement it for some time series stuff. When I did that, use Derman and Koopman's book. Yes, so there's a couple books on Kalman filters. I admittedly have not read, frankly, any of them. And I've only skimmed through ProbML. I was mostly learning it through the applied library. And I'll talk about why in a second. When I've been learning Kalman filters, I constantly struggle through a couple of the things. But let us get to the code and it'll make more sense. Yuri's done common filter and variations. All right, so I'm not going to belabor common filters too much. I'm going to focus more on Dynamax. So then my second question is, how many of you have used common filters in Dynamax particularly? Let me know that as well as I talk through this. So let's fire up this Jupyter Notebook, and I'll talk through the agenda. Always shooting to make this less than 45 minutes. Definitely less, well, likely 45 minutes, less than an hour ideally. And then sometimes we go over. Oops, this is the wrong directory. Theo, no Dynamax yet. Okay, great. At least Theo will be seeing something new, and I will not be boring you all. So we're on our same GitHub repository. If anybody wants me to link it, let's go ahead. Just let me know. Let's just jump straight into our slides here. I'm going to total aside while we're talking about hardware. I'm going to upgrade my secondary hard drive to a solid state drive so it isn't so slow for you folks. I know it's occasionally been a little slow in this Jupyter Notebook. All right. So linear Gaussian state space models. You know we're going to be using Dynamax because I have all of the imports here. So I kept the imports in on this time on purpose because they're quite interesting. In Dynamax, we use a couple of things actually. The Jacks NumPy sampler, the Jacks NumPy interface and the Jacks random sampler are used extensively throughout Kevin's docs, and they're quite useful in conjunction with the Dynamax API itself. And then in Dynamax, probably should have done this in a certain order, but you have the linear Gaussian state space model sort of definition class, which we'll see in a second, will give us our parameters and some samples. And then we have the smoother and the filter, very, very similar, actually exactly similar to what we had in the discrete hidden Markov models, if you haven't forgotten about those already. And then I imported these, but I actually don't even think I used them. But let's go through it. So our agenda, we're going to talk about linear Gaussian state space models, key difference between our discrete state space models. Since you folks are already familiar with linear Gaussian state space models here, I'm not going to, again, belabor this. We'll talk through Roger Labe's common filter book. This is actually the common filter book that I've used the most. You'll see why in a second. I'm going to re-implement the 1D dog example in Dynamax. It's a basic example, but it actually highlights a lot of, I don't want to say sharp edges, but it's a good contrast. I actually think it's a great contrast between a very basic common filter example, the introductory example of Roger Labe's book, and then the what can be done with common filters and the Dynamax API. And then I'll just briefly go through state space linear regression. There's actually one other item I've been put on here real quick, which was Jacks, VMAP, and PMAP. So similarly, because we have a nice small group today, let me know how many of you have used Jacks, VMAP, and PMAP before. I have a notebook on that. I can talk through that as well, particularly because it has some relevance to the common filter code we're going to be going through. So let me know about Jacks while I'm talking, and let's jump into it. So the book I'm going to be referring to, if you folks haven't seen, is Roger Labe's book. Let's go to it. Do I not have internet on this computer? That's going to be a bummer. Huh. All right. Well, so this is sometimes what happens with technology. All right. Let me set up real quick to use my personal computer in a second. I'm just gonna see what's up. All right. If you're seeing a black screen, that's on purpose. We are now jumping to this window is in my personal computer, which does have internet, not the virtual machine. So we're going to be using Roger Labe's book, just for a brief example. For those who have not seen it, I actually think this is especially for practitioners, this is a particularly good book. Since we're here, I'll explain why I use this book. Two reasons. One is I've friends with Alan Downey, and he's recommended this book. He has a wonderful series of videos. Let me turn my capture card on. He has a wonderful series of books, which at some point maybe we'll go through. But excellent author, and any book recommendation from Alan is going to be great. He's a prolific author. The second reason, though, is Sam Rodkey was my colleague at SpaceX. He worked in the flight software department, and we used common filters a lot at SpaceX, like a lot, for a lot of reasons. Common filters have been used in the space industry for decades, as I have alluded, and we definitely use them at SpaceX. And we use this particular text, so that's why I've seen this text before. What we're particularly interested in for this book club is this this particular chapter. For the folks who have done common filters before, this is going to be maybe I don't want to say boring, but basic chapter. What we are interested in is, there's a dog example in here. I think it was near the top. It's this one. It's this one right here, where we were trying to find the Gaussian belief of a dog's movement, and it is this plot. So this is a one-dimensional example. The dog moves mostly forward, could move backwards theoretically, and also there's sensor noise in any classic common filter problem and state space model problem. The state is where the dog is. Actually, I have to remember, yes, the state. Okay, we're going to go back because I always mess this up. But between where the dog is and the measurement, you have the state and you have the space with some noise. So jumping back to our virtual window. In Roger Labbe's book, he has this diagram, which I also find to be a very nice diagram of state space models. You have an initial condition. You're predicting in this case, where the dog is. The dog moves. You take a measurement. You then update your predictions. Actually, this helps because you get the state estimate, which is where the dog is, and the space is the actual. Oh man, I'm always gonna mess this up. So I'm too jet lagged to remember state and space at the moment, but between the state and the space, you have both. This I actually found to be a really nice picture as well from Roger Labbe's book. Again, a basic example of how state space models work, but particularly it's nice with a physical example, which we don't get. We don't get a lot in some of the other books, but essentially this is the weight example from Roger Labbe's book. We have a weight. You make a prediction of what the next time step is going to be in the next day. You get a measurement, and your estimate is between your prediction and your noisy measurement. It's a very intuitive example between how we would probably do things as a human. You have what you believe, you have what the measurement is, and if you believe the measurement has a noise, your belief will probably be between your prediction and the measurement, but not outside. So really key piece of intuition. I just covered that we're going to talk about this example, and what I'm going to do is I'm going to jump out of this notebook, jump out of the slideshow and talk through it from Roger Labbe's book. So in Roger Labbe's book, they don't use Dynamax. In this case, he actually breaks the common filter down and uses it analytically. So his analytical solution looks like this. Given that folks here are well familiar with common filters, I'm not going to cover this in great detail at the moment, unless somebody wants me to. So if somebody here wants me to talk through this in greater detail, I'm going to take a quick pass, and then we can go through it again. But essentially, in that book, you have a dynamics model. You have what the dog is doing. The dog is moving. You have the mean and variance of its actual movements. And then you have some sensor variance. So two things are happening here. There's two sources of variation. And when I was learning common filters, it took me a long time to wrap my head around. you have the variance in the actual movement of the world. So when we were launching rockets at SpaceX, you have the variance of like where the rocket actually is. That's just from the nature of the engine thrust is different, or there's more wind resistance, or there's wind can push the vehicle one way or another. There's a lot of forces that are happening on the vehicle. And then you have the various sensors on the vehicle that also have their own set of noise. Typically in aircrafts and maybe rockets, I don't know if I'm supposed to say that, but you have multiple sensors that are all providing multiple updates. It's one could be faulty. That's, I mean, the most obvious case. One could just break, but also they're all have certain amounts of noise. So between the different sensors, if you have more measurements, you can more easily extrapolate, or sorry, maybe interpolate where the vehicle actually is. Often you have different types of sensors as well. This is a whole other thing. But you have the GPS is one sensor truth, and then you also have IMU sensors. This also is very common in how navigation units work within, like, let's say your phone these days. You get external sensors like the GPS, which tells you where you are, but then there's also sensors that are occurring within the phone. So this is how it like Google Maps or Apple Maps continues to work within a tunnel. Another good example of common filters. All right, so real world examples aside, in Roger Labe's book, you end up with this. So he starts with a mean of 0 for where the dog is at, and then a variance of 400. So we assume the dog is anywhere between 1,000 and, sorry, let me word this more carefully. We really don't know where the dog is given this variance, right? The dog could be 1,000 meters negative, it could be 1,000 meters positive, or feet, or whatever the unit is. But as soon as it starts moving and we start taking sensor measurements, we start really honing in on where this particular dog is. At first, the variance is fairly high because we've just taken one measurement. But as we take more and more measurements with our greatly calibrated sensor, which is better than our initial guess, we end up figuring out where the dog is. Now, what's important is, and a key point here is that we're using the analytical formulas. This is the reason state space models, and particularly common filters, have been used for a long time. The math just works out analytically that it's awesome, and you can just implement it in this function. So that's all well and good. But now we have Dynamax. So what I wanted to do with Dynamax is, I'll have to jump back to the docs. What we had this week in the Dynamax docs is we had this particular example, and in this particular example, it's I shouldn't say 2D example, because it's a 40 space. It's a 40 hidden state between hidden positions and hidden velocities. Sorry, I shouldn't say 40. I apologize. It is a 4x4 matrix in 2 dimensions. The jet lag. Sorry about that. And then you have the output is 2 dimensions. The output is a 2x2 matrix of the position of this thing. So it could be in some position in the I don't want to say X because now we're getting into something here. It could be in this Y dimension in one area and in this dimension in another area. The reason I'm not saying X is because there are going to be a lot of variable names. This was one point of confusion I had for a bit. It's not X and Y in this particular notebook, but it's like Y1 and Y2. And in fact, they actually don't even use Y. They use U and V, which was confusing for me for another thing because V could be velocity. But we're going to get into Dynamax in a second, some of the challenges with this particular notebook. But the point being is that instead of using an analytical formula like we had over here, we instead have to construct a lot of matrices to get the Dynamax API to work. So we have to put our Dynamax model in a particular form. We're going to have to put our initial conditions and everything in a particular form. And that's how we end up with with our code. So jumping back real quick to the Dynamax Notebook, in their example, they've already done this for us in the docs. They've created the initial conditions because the hidden state is a 1x4, 4x1. So, you have four things for each one of the states, both the positions in each dimension, and then also the velocity in each dimension. In this case, the position theoretically started out at 8 and 10, and then 1 and 0 for the velocity. So the velocity is only going for one of the dimensions. It's staying still. And then you have the dynamics weights, and then you have the covariance for the dynamics. So the dynamics are describing how the system is moving under the hood. In this case, we have velocity and position movement. This will be a good contrast to our our linear regression example we'll have in a second. And then we have the emissions. So this is what you see. I'm sorry, this is not what you see. This is just how the emissions relate to the dynamics. And then you have the rest of the notebook. I'm going to point out my explanation of this is confusing, and I would not use it as a reference. You're really going to have to go through the code to get this one. It'll be tough for me to explain smoothly, especially with the notebook is written now, because I'm going to show you something else. All that aside, this plot is maybe not surprising because you folks have used Kalman filters, but essentially we have our true state, which is just a straight movement down the waves, and then you have the filtered means, which is what we would estimate as we're moving along, and this is like, let's say, a SpaceX rocket moving through the world, and then you also have the uncertainty circles of where it's at. So I actually found this to be a nice helper function that has been included in Dynamax, even if you're not using. I actually don't know if it'll not work with other things that are not Dynamax, but if you are using Dynamax, it's very nice that they have not only the estimation code written for you, but also this helper function that helps you see what's going on. It's certainly something that I wish I had when I was working at SpaceX, because I had to write all this code in by hand. Now, with that being said, there were a number of points about this notebook that were confusing that are actually still here, and then what Theo had mentioned. So Theo had said in the book they use xt1 and xt2 and x dot, so it's even more confusing. Yes, that is one point of confusion that I had. Certainly, it's also not the same as Roger Labe's book, so that was another point of confusion. But the biggest point of confusion I had in this entire thing, which I'm just going to show you because this tripped me up for a long time. I should just go back here. Is surprise. I'm pretty sure the docs are wrong. Well, I think they mismatch. So there's what was represented in LaTeX up at the top, and then what was represented in the code had different ordering along the column vector. So okay. Theo says the docs are wrong. Great. I'm glad you saw that. This tripped me up for a really long time because I was reading the LaTeX and then I was modifying the code with this in mind, and then I was trying to run it in our dog example, and it was just not working. So that was the first thing that really took me for a loop. If you folks want to see my whole journey here, I closed an issue ticket, but anyhow, that was one. So I'd say that was docs being wrong is, okay, we can fix that. They're not a challenge, but the actual challenge, which is more useful for us to talk about, is shapes. So Dynamax, there are libraries like, let's say PyMC, where if you input 1D arrays or you have shapes that are a certain way, it'll figure it out for you. Like, I won't go through a PyMC example right now, but in PyMC, if you put in a vector that's a single, that's 1D, and then if you put in a vector that's 2D, in most cases, PyMC under the hood will just like figure out that to make the math work in the way it's written with like Cholesky's and all this stuff that's going on under the hood, that it needs to expand the 1D representation to 2D. So it has all these like a PyMC in its code base has all these at least 1D or at least 2Ds all within the code base. Within Dynamax, that was not the case. So with a 1D example, and I invite you to try this. I won't do it right now to bother you. But if you do things like in our case, the emissions were just a 1D array, or the in this case there's really no covariance between the velocity sensor and the position sensor because we only have a position sensor on the dog. If you try doing that, Dynamax will throw all sorts of errors. It's hard to tell what they are unless you read the code carefully and go through and see which particular steps are failing. So what I had to do in Dynamax was I had to split this problem up in two things. I had to first, actually three things. I had to first figure out the parameters it would initialize with. This was pretty permissive, but it would initialize with a lot of things, which was nice, but not everything. But eventually I figured out the set that it would initialize with. Then I had to go through a set of prior sampling where I had to check if the priors would work. And I believe the priors use the dynamics in the initial means and not so much the some of the emission matrices, but it was then the step of getting prior sampling working. In this case, prior sampling has obviously worked. And now we have our results. So in this case, the dog moves exactly like Roger Labe's book at a velocity of about one unit per second. Now, another thing in the docs that was not super well explained that I want to talk about as well while we're here is in the Dynamax docs, there's a whole layer of getting Jacks to work. So some of these where is it? Some of these multiplications, like this covariance, like this one, is the just make sure that in this particular example we move largely in one direction and not a lot in the other direction. So this very, very small 0.01001 is to get particular dynamics movement. But then there's also this one, which confused me for a while until I ran into the example. This essentially is taking Jacks NumPy ints and then turning them into floats, like in a clever implicit manner. Because what happens is if you don't do this, Jacks will throw a bunch of errors. So once you've made it past the shape errors, then you also have a series of Jacks errors. This isn't on Dynamax, but you need in Jacks you need everything to be the right type of representation in the under the hood. So whether it's an int or float 32 or float 64, or whether it's a Jacks array or whether it's a NumPy array, all this is required for Jacks to be able to do the numerical speedups that it does. So there were again 4 distinct steps to really get this example to work for me. It was in order again, just so we explain it. It was 1, getting the shapes right to get the initialization of the linear Gaussian state space model to work. Then the shapes right to get prior sampling to work. Then the shapes right to get actual sampling to work. And then also then just the Jack stuff to get Jacks to sample with it. So that's been my experience with Dynamax on this particular problem. I'll also say there was although this is the working example where the dog is moving indeed at about 1 unit per second with the velocity and its actual position. If you don't set up this dynamics model correctly and you transpose one of these shapes, or you get the shape wrong, I forgot which one I did, everything will work, but your whole model, everything will just be wrong. I was getting values that did not match what was supposed to be happening, but nothing was wrong in the specification of the numbers, but there was something wrong in the specification of the matrix shapes. So my 5th step that I would put on here, if you're using Dynamax, is before you use it on real world examples, uh, construct your own fake example with fake data, and um, just like we did in this dog example, where you have just some data that you know what the inputs were and what the states were, to then verify that when you actually run it on your actual data, you get what you want. The summarization here is that Dynamax doesn't have a lot of safeties built into the library. It's not a bad thing necessarily. It's a library that just came out recently. It's written by researchers that really know the code. It seems like the users of Dynamax right now are the library authors themselves in large part. So these rough edges come up where the docs are subtly wrong, or there's not a lot of safeties built into the library, as opposed to PyMC, where we have in PyMC, it's been a mature code base that's been used for, at this point, decades, if you count all the way back to the original PyMC. And a lot of users of PyMC are not, let's say, Bayesians that have been working for decades. So there's a lot of safeties that are built into the library. It's the same thing with like scikit-learn, for instance. When you use scikit-learn or even TensorFlow, these are libraries that have now included all the safeties and warnings and things like that for end users that aren't necessarily super great practitioners of neural nets or machine learning at the moment. So it's just like a car, right? In modern cars, you've got seatbelts and warnings and things like that, but Dynamax is more of like that hot rod roadster that you see somebody driving around that they constructed in their garage. Not a lot of airbags in there. Seatbelts because they're required by law, but when things go wrong, you don't have a lot of sensors and whatnot telling you what's happening. Dynamax is more like the hot rod roadster for the weekend. All right. So Dynamax learnings, documentation can be wrong. It's real picky about shapes. You can try modifying any of these shapes and seeing what happens. It might be a good test example for those who are going to dive into Dynamax some more. The other thing I wanted to talk about while we are on Dynamax, before I get there, if there are any questions, of course, on this 1D dog move example, let me know. I will also address those. But for the moment, I will jump into linear regression. So this I thought was a cool pedagogical example from both ProbML and also from the Dynamax docs. It's that you can essentially do a linear regression with a state space model. So state space models are quite flexible. We're going to see them used in many examples. We already saw them used for discrete cases, but in continuous cases, if you just make the assumption that there's no parameter noise, there's only measurement noise, and the parameters stay largely the same from one to one, from one state to the next, you can create what's a linear regression, and all the math will just work out for this to be exactly a linear regression. So I'll let the ProbML and this notebook teach you it rather than me talking through it. But it's again just a really neat. It's a really neat example of what happens as you turn things on and off, let's say, in a state space model, and particularly a linear Gaussian state space model. There's a lot of stuff going on, and to bring up to talk about that. So when I say there's a lot of stuff going on, there is a lot of stuff going on in the Dynamax implementation linear Gaussian state space models. So when you go to Roger Lawbay's book and we talk about this dog example, there's not too many, let's say, knobs to turn. You have a very basic Dynamax model. The dog is moving in one dimension, so the math really just works out that you take the previous position and add some stuff. The sensor noise is really only in one dimension, so there isn't another dimension to have any noise in. The emissions and the dynamics are, again, very straightforward. And then what was the last thing? There's no bias, and there's one other thing that was taken out. Anyhow, the reason that if we go back to this is that is in Dynamax, you have a lot more stuff to configure or potentially configure. Here's the whole list of it. It's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So 13 things to initialize this particular model. It's not a bad thing. It means that this library is super flexible. You can really represent tons of different problems in Dynamax. And not only can you do it in 1D, which is the case in the Bayesian filters, Kalman filters in, it's a very long time, Kalman and Bayesian filters in Python. It's that all of these have covariances as well. So you can do all sorts of things which we had seen in the dog example that I just brushed over. There could be covariances in the initial position. There could be covariances in the dynamics model. There could be covariances in the emissions. And there's additional covariances for other things. There also is included a bias factor in here as well, which we didn't implement in the code, but there could be inputs and state weight biases. So really this library has a lot of configurable parameters. If I'm going to be doing linear Gaussian state space models in practice, even if I don't need them to be computationally sped up, I'm probably going to be using Dynamax in the future because it's, I think other libraries make assumptions of the problems you're trying to work on, which is good because then it subsets the API to be sort of plug and play with what you need. But then if anything changes, like we then assume, or that we then have covariance, correlated noises or correlated dynamics or correlated emissions, we can't represent those in those libraries from what I've seen in the past. But Dynamax lets you do all of it. So it's really neat there. Okay, that is my talk on at least just Dynamax. We're coming up on 45 minutes, so I'm going to next talk about Jacks, VMAP and PMAP, and how they relate to everything we just talked about. As always, if you have questions about Dynamax or linear Gaussian state space models, let me know. I'm always curious because I'm also looking to update my sort of state and position of this book club, of whether you wanted me to bring up more ProbML or anything else, or whether we're now hitting sort of our cruising altitude of code and application. But while you think about that, let me jump into the very last notebook we have, which is Jacks itself. And my virtual computer shut off, at least when the screen saving mode. All right. So let us get to, I should have put this in the Jacks folder, but I didn't. Vectorization and parallelization. So Dynamax, as we've talked about many times, is built on Jacks, this library which does computational speedups. Jacks does a lot of things to make computational speedups quite nice and smooth. And two of the things it does is automatic vectorization and really easy device parallelization. So I'm going to have to copy these. I'm going to have to do this all in my personal computer. So let's flip back to that. All right. GitHub.com. Let's go to my state space model. Book club. LGSSMs. Vectorization and parallelization. So before I go too deeply into vectorization and parallelization, could folks let me know who here, if I say the words vectorization in the context of NumPy, and, well, I should say computational computing, vectorization and parallelization, like who understands what those mean? If you folks all tell me you know what they mean, I won't talk about them in super great detail. But if you folks don't know what they mean, then I'll cover them more. So in Dynamax, we'll start there. There's a couple of places where this is used. The third notebook was parallel filtering and smoothing in linear Gaussian state space models. Where this would be used, the most obvious example is you have multiple dogs. Let's say you're a dog walker and you've got 10 dogs and you need to estimate where all of them are at the same time. Um, if you're going to do that computationally, it doesn't make sense to do them serially. I mean, it's a common problem. You would want the computer to do them all at the same time in parallel. I'm going to point out SpaceX has a lot of satellites in space now, like a ton of satellites in space, thousands at this point. And updating the position sequentially wouldn't work very well, because by the time you've done the calculation to figure out where the first one is, by the time you've gone through all 4 or 5,000, the first one's already moved. So in physical applications where there's a bunch of objects being tracked, like by the time the computation finishes, if you're doing it in serial, you've already lost track of the first thing. So you can't do that. So it's nice to be able to do things in parallel, and Dynamax makes that quite simple because they've got an API for it. It's called a parallel LGSM smoother. As you may guess, it parallelizes the smoothing algorithm. And they have these nice plots here showing you how the timing works. So you've got the serial version, which stays the same as the sequence gets longer, stays about the same. And then you got the parallel one, which tends to speed up. What I really thought was better than the plots was this. For the number of time steps, it shows you how this thing speeds up computation. So from the Dynamax level, what is happening differently under... Oh, I'm not even showing my window. Man, classic mistake. Let me show you this again. Here's the notebook I was looking at, parallel filtering and smoothing in LGSSMs, and then how you can reduce the cost of inference. Now, an interesting thing, I should have mentioned this as well, is that this seems to be on a single time series, so it's actually kind of cool that it speeds it up just for a single time series, but you can imagine the same thing for many things at once. In the Dynamax code, if you go to the parallel inference module and the class definition, you'll see that they use VMAP here, and you won't find VMAP in the original inference for LGSSM, for linear Gaussian state space model. So there is no VMAP in here, but there is a VMAP in here, which is kind of cool that you can just take your code for the most part and then just VMAP it, and it'll just work. It's actually a really neat thing for Jacks. So a ton of things have come in on the chat. Let's jump to the chat super quick. Let's go chat overlay. Theo says, once you do derivation for the joint conditional properties, they're all the same, and assume Dynamax implemented the matrix multiplication correctly. Yep. So I had just shown that in the screen, but I will show that in the screen in a second. Happy with vectorization and parallelization. I don't know, Theo, whether you meant that you're happy for me to talk about it, or you're happy and you already know about it. So let me know about that. Charles says familiar, but not with PMAP and VMAP and Jacks. All right, Charlie. Charlie. I will talk about PMAP and VMAP and Jacks because it does some neat things. And then Theo says I'm not sharing my screen. Yes, I'm sorry about that. That's another one of the things that to keep track of in this entire orchestration. I hear other streamers have crews behind them that do all this and get all this stuff working, like a TV crew, but I'm just a one-man show here. To Theo's point, if you want to see the math behind Dynamax, they do all the matrix multiplication in here under the hood. It's quite good to look at, but I'm also going to point out I ended up having to look through this because of all of the shape problems I was having. So when I had talked about shape problems earlier between the emissions matrix and let's say the dynamics matrix not working out, or the dynamics and initial conditions, I ended up having to just read all of this to get my shapes to work and add a bunch of debugging statements. So just quite practically speaking, if you're going to use Dynamax, I almost guarantee you're going to end up reading these codes if not directly, in the form of error messages, exception messages that pop up when you try and run things, and then the shapes don't work out and you get errors. So the nice thing is that it's all very well organized. You just go to this state space model, linear Gaussian state space model directory. They have the demos in there, they have the models in there, and you can fairly readily figure out what part of your code is failing and where you need to work, what you need to work on. And if you're like the folks here who are already familiar with state space models, it's quite easy to read. So another benefit of Dynamax, it's not this massive library that's got all this stuff going on. It's very well written and organized. So even though it doesn't come with a lot of safeties under the hood, it does mean that you can quickly diagnose by diving into the code itself. All right, so jumping back to Jacks and parallelization real quick, because that is our very last topic. So there's two things. Vectorization, in short, is in NumPy is if you write your code in a particular way, it allows NumPy to just like speed it up. So a good example could be is like matrix multiplication. It's the easiest example. You could do matrix multiplication by writing a for loop that just takes one thing and then actually here's a good example. Here's well, that's not a good example. I'm sorry. You could write matrix multiplication where each element is multiplied in a for loop, like a double for loop. I don't have an example. Let's find a matrix. Okay, so you could write an example. You could write a double for loop, as a basic Python example where you take this and you multiply this and you multiply this and you multiply this and you multiply this, and then you go to the next one and you multiply this and you multiply this. And so that would take forever. That's why we have NumPy. When you multiply two matrices together using this at operator in NumPy, or just the dot product the dot product method or any of that, it's what's called vectorized under the hood, where NumPy does a lot of fancy things. Essentially, let's say fancy things, to then take that what would have been a double for loop and either consolidate it down into removing a for loop, and then also then being able to compile it to a lower level representation of code that makes it even better. So usually two things are going on. One is compiling it to a lower level code that can execute faster than Python for loops, and then also in special cases, it can also then remove axes of computation by doing clever computational tricks. In Jacks, the trouble is you have to be particularly good at, let's say, NumPy magic to be able to do this correctly. And so here's an example where this is done manually. Let's say we want to multiply two things together, calculate the convolution of two one-dimensional vectors. In this case, we have this 1D vector and this 1D vector. You need to know that this is sort of the way to write it, and then it would work out in NumPy or Jacks NumPy. But the nice thing with Jacks is you can automatically do this. Where's the VMAP? In Jacks, you can automatically do this by calling VMAP on a particular portion of code, and it'll magically figure out the vectorization. So I won't take the time to go through this notebook again live because we're coming up on an hour, but I invite you to look at this notebook in Jacks and see the naive ways of doing this and producing the correct results, all the work it takes to then manually vectorize it, and then just the difference of calling VMAP, jacks.vmap on your function, and it just magically figures out what's called the batch dimension, just labeled right here, and then makes it a vectorized piece of code. Another cool part is they don't show this here, but you don't have to then assign it to auto batch convolve like this. It has this Jacks has this this decorator, which was the at VMAP I showed you earlier. Oh, so actually they call it twice? Okay, so one in this is a good example in Dynamax when it's they use the functional form of VMAP. So this has been vectorized quite automagically over a set of dimensions using the VMAP function, and then this has been vectorized using the VMAP decorator. So you don't have to then assign this to another arbitrary function name. You just take your smoothing operator and it's you get the vectorized version when you import from Dynamax. So vectorization is cool in and of itself. This makes things faster on a single. Okay, I can't say single CPU because CPUs now have parallel stuff going on, but it essentially makes I think faster for single thread, and I want to say single thread. That might be wrong, but I think we're gonna come back to this point about multiple devices when we talk about parallelization, which is going to be right here. So the second thing we can do with computers is modern computers don't just have sometimes one GPU or even one TPU or one CPU, and even within the CPU there could be multiple things, multiple threads. What Jacks allows us to do is we can also get parallel evaluation quite simply for free to take care of it. Single program multi data code. So let's say I can't do this on my computer because I don't have 8 TPUs in my computer, but when I'm working at Google, I have access to computers that have a lot of TPUs in them, and I want to do things quite quickly. Since I have access to computers that are very different than the computers that I have at home, you end up seeing, because I do, and then also my coworkers do, you end up seeing a lot of code with Jacks VMAP and Jacks PMAP in it a lot, because now we can take something, we can run it on Google's internal cluster, and what we can do is we can split that computation up among a cloud of computers, and even if it's a single computer, it could have a lot of different devices in there. And so the way PMAP works is very similar to VMAP. Let me find you an example. Where is it? Here's PMAP being used as the functional operator, and I also believe it can be used as a decorator, which I'm not seeing here. Okay, so we'll just stick with the functional form. But again, you just take your your regular function, and then you call PMAP on it, and suddenly not only do you have code that is running vectorized on a single device, it is now can be split up in parallel among multiple devices that Jacks has automatically recognized. So you don't have to worry about any of the overhead in maintaining the code that splits up the computation, waits for the result, and then pulls it back in and combines the result. Jacks just handles all that for you. So again, the reason this is quite cool is that if you're going to do, let's say, a real world example that I would bring up about this is you can use common filters to track, let's say, user behavior over time. So it could be how long a user is using an app, or like where are they moving in a 2D embedded space. When I was working at Sweetgreen, and we had the data department there, this is a kind of funny example. I'm just going to talk you through it because this is it's one of the most interesting data problems I've worked at, because it's a thing that nobody thinks about as a data problem, but we turned it into a data problem. So let's say, let me show you. So for those who haven't been to Sweetgreen, there's essentially two types of salads. There's let's say cold salads is like one dimension, and then there's warm salads. These are the human classified versions, but then there's also versions of salads that have they have cheese in them or dairy in them, or versions that don't. And what we have done is another thing to point out about Sweetgreen is any one of these you can customize. So let's say I want to order guacamole greens for whatever reason. You can go in and you can remove things. Like I can take stuff out arbitrarily and I can add stuff in arbitrarily. So what would happen in practice is that customers would very rarely order the off-the-shelf item. They would customize it a whole bunch. So we had, and actually here's another point to bring up, is that at Sweetgreen season out, like real seasons mattered a lot. People in New York would have very different ordering behavior than they would in summer. As you can imagine, when it's freezing outside, you're probably going to want to eat a very different thing than when it's warm in the summer. So what we had done is we had taken every salad order that had ever existed and created like a sort of embedding space of salads. And we were then running all sorts of analytics at the time on this embedding space. And something that I hadn't done, but we could do with common filters, is you could track the trend of somebody's salad ordering behavior over time using common filters. So I suppose we could turn it into like a 4D problem or 8D problem of what's like this person's salad ordering behavior in this embedded space of salads. And the reason I bring this up with PMAP is that we have lots of customers at Sweetgreen, like hundreds of thousands. And so if I wanted to do that quickly, let's say I wanted to estimate where somebody was going to be in salad embedding space, and I want to do it as an overnight job, what I would have done is I would have used a library like Dynamax, and I would have VMapped and PMapped this problem and thrown it up on one of our AWS clusters. So then I could then at the same time hopefully quickly figure out where customer behavior was trending for all customers, essentially running like hundreds of thousands of common filters for people's salad ordering behavior at the same time. So that's my my real world example of how I could use common filters when I worked at the salad company. So it was an interesting problem to me because people don't typically, when I work at SpaceX and Google, the problems are much more obvious, and people tend to expect that I'm using data and the problems are quite, again, obvious. But at Sweetgreen, the problems weren't so obvious. It was quite interesting actually taking mathematics that are not really used in restaurant companies and trying to use it at a restaurant company. So Yuri asks now, is there a good reason to use common filters for the salad problem instead of the moving average? Honestly, Yuri, I actually think so. I think yes. So it comes back to like, why do we use common filters at all? And I'm gonna pull up Roger Labe's example. Essentially, the question you're asking is like, why don't we use moving averages for any problem instead of using the common filter model? So like, why don't we just take the dog's position by taking a series of moving averages? And you're right. We could just take the moving average, but then if I talk that problem out in my head, then it'd be like, what's the moving average window? Is there dynamics to the problem, which is your second question here? Is there's no guidance laws of forces? So in the solid example, you're right. There's no Newton's laws of motions that are constraining how this motion should work. Like there's no physics to this problem, so it's less, maybe let's say, applicable. But we could say the same about the weight example that Roger Labe uses at the beginning as well. There's no like rule that your weight loss has to follow Newtonian mechanics, but I think there is the sense that your weight loss isn't. It's going to be. There's a reason this problem is interesting, which I'll talk about in a second. But there isn't. We would surmise that your weight loss would follow some sort of curve or sort of trajectory that maybe it just won't be. That there's some sort of dynamics under the hood. So I'm making that same assumption with the Sweetgreen users, with a common filter. Then perhaps is that there's some sort of dynamics to the problem. So that's all to say, to give you a really weak answer at the end, is that perhaps a moving average would have been fine at Sweetgreen. I didn't run either moving average or common filter, but in the future, you could do either. Right now, there's if I assume that there's no dynamics and I'm okay with the downsides of a moving average, then sure, I'll use a moving average. But in the real world, Maybe I assume that there's some dynamics to the problem. Another reason I'm thinking through this example in my head is there are particular problems at Google where you could use a moving average, and we have the moving average as the baseline, but then we use common filters on top of it, even though that's not a situation has dynamics in it. So I don't work in Google Maps. I work in the trust and safety department at Google, which neither trust nor safety are bound by the laws of physics. They're both human-made concepts, and the things that we do at Google also the operational systems that I work on are not bound by the laws of dynamics, but we still use common filters in some of those estimation problems, because the common filter does the very nice thing that we talked about at the beginning, which was let's see if we can find it, which it does this, right, which a moving average doesn't do. We have a last estimated position, we have a prediction, and it does this nice sort of averaging in a way that a moving average doesn't. So that's my like 3-part answer, Yuri, is you're right, we could use either moving average or a common filter. There's no dynamics to the problem that's like forcing us to think one way or another, but there have been cases in the either both made up about this weight example here, or in the real world where common filters tend to be more flexible in the way they make estimations, so I can tune the model to be a certain way. With moving average, really the only thing you can tune is the number of data points that you use in the average, and you end up with really weird stuff like once an outlier drops off, for instance, or if an outlier enters a moving average, right, it can change that average quite dramatically. I guess I could use mean average, the moving median at that point, maybe, but then even then, it's like the sliding window is suspect to like outliers, things like that, even in spaces that are not bound by physical constraints. All right. Whew. That's really, I really appreciate you asking that question, though. That's honestly the question that everyone should be asking before they're using common filters, is like, could I use a moving average? And then why would a common filter be better than a moving average? Like even for systems like these, like, it's worth asking the question, why don't you just use the moving average? Why would I need to jump to a common filter immediately? For rockets, we really needed to be sure where that rocket was, like super needed to know where that rocket was. And it was obviously bound by the laws of physics. So it like just made sense to use a common filter, because we just really needed to be able to tune that model. And then also we very obviously had a dynamic system where you very obviously knew that position plus velocity plus times time was like where that thing was going to be. Yuri says, thank you. Every time I'm doing smoothing outside of signal processing, I'm trying to figure out what to use. So Yuri, I guess you can use, add common filters to the list of things you can use. I believe common filters are used. Well, I mean, I know common filters are used in signal processing. All right, great. So we are slightly over an hour. I'm always underestimating the amount of time these things will take. As always, let me know whether the hour is useful. I always want to be sensitive for your time. The last thing while you think about that is we're just going to keep chugging right along in our book club. And we're going to go... Well, I want to point out two things. Is I didn't talk about map estimation and Bayesian estimation for LGSSM, linear Gaussian state space models. And to be quite frank, I actually don't know why you would use Bayesian parameter estimation for state space models, given that the analytical formula works really, really well. But what I might do one of two things. So we're gonna say the definite thing, and then we're gonna go with the uncertain thing. So the definite thing is we're gonna continue moving on in this book club by talking through extended, scented, and unscented common filters. I will ask you folks in the discourse to post whether you're, again, familiar with extended and unscented common filters, so I know how much time to spend on the philosophy. Otherwise, we're going to do the same thing we did today, which is largely focus on the code. But we're going to try and go through these 3 notebooks next. Let's give ourselves at least, let's say 3 weeks for this one. So if I look at my calendar, that would mean that we're going to come back here on the 23rd of April, back on a faster schedule because I don't have any vacation planned this week. And then what I may do, this is the uncertain thing, is that I may do a session before the 23rd. So either on the 9th or the 16th, probably the 16th, where we talk about the parameter estimation, the map estimation, maximum a posteriori estimation, and then the Bayesian parameter estimation. A much shorter section where we're not going to be talking about the common filters in detail. Not, I probably won't have so many examples, but where we particularly talk about linear Gauss, the map estimation that's available in common filters, and then we talk about Jacks as a library. And actually, the very last question I have for you is why we talk about Jacks. I am actually biased towards liking Jacks because I am a contributor to Jacks. I guess number 3 on the list. So if you folks are curious about Jacks, we can actually we could definitely do a single session on this, but it's even just interesting as a secondary book club topic. So you folks let me know whether you want me to talk about Jacks in its own session. Obviously it's connected to Dynamax here, but it's also just a very interesting library in its own right, maybe a good tangent at the minimum. And I can talk to you about this library, Hamiltonian Monte Carlo, and what's going on here. So that actually ends up with 3 things. I will again post in the discourse. So again, 100% certain we are going to be going through nonlinear Gaussian state space models, and we're going to do that on April 23rd. I will create a discourse topic on that, and of course a new category on that. And then optionally, if folks want, we can talk about these 2 notebooks before then. And the third thing is, if you really want me to talk about Jacks, I could talk about Jacks for hours, but I'll make it smoother. I can also dive deeper into Jacks itself as a library, not just the surface level overview that we're going to get from Dynamax. All right. That's all I have for today. I'm going to go through all these questions that you guys have here. All right. Yuri says, thank you. Thank you. Hoping SpaceX use some nonlinear filters as well. I won't say, but we use a lot of filters. Tyler says, my dumb self mixed up time zones and I logged in. We'll catch up. Okay. Well, Tyler, it's good to see you. I was wondering how many people would forget about this book club in the last month, and I'm glad to see that not everybody forgot, that we still have the regular crew around. So I'm really glad to see you folks back. It's quite nice to be back. And then Theo says, I think a short book club on sampling algorithms using Jacks would be cool. Maybe after their sampling book is done. Yeah, I think maybe sampling. I think a couple sessions on sampling would be cool. So I might do a book club. I don't know when they're gonna finish their book, so I'm kind of thinking it through in my head. But yeah, okay. That's the more general point is what should we do after ProbML or after common filters. So going back to the webcam real quick, we have really only 2 or 3 more sessions left between nonlinear Gaussian state space models and then generalized Gaussian state space models. But start thinking about what you'd like to see in a book club, and again, whether you'd like to see this book club then move to another topic. We're on causal inference, and now we're on state space models and ProbML, and then we'll have a third thing. I don't want to take up more and more of your time, but in the last 3 minutes, I was thinking large language models because they're just becoming so prevalent. For me, they're showing up everywhere at work, at Google, and they're also showing up in my personal life, just on everything. They've also been honestly quite useful. I've been using them, let's say, as a naive practitioner, and so they'd be good to talk about, just because they're, I don't know, I feel like they're going to be everywhere. But also, a lot of people have talked about large language models already. There's a lot of material out there, so you could go back and forth. Anyhow, that's a problem for a farther future from now, maybe a month or two down the road. For now, thank you again for coming to this linear Gaussian state space model book club. Thank you, Chad, for dealing with audio problems in the complex processing pipeline from my room to your room in Oregon, and looking forward to seeing you folks again in a couple of weeks here, at least at maximum 3 weeks, maybe a little bit shorter. You know where to find everything. It's all on in the discourse. Show that real quick for those who don't know, but it's all in the discourse. I'll post new threads, new topics, and send out new emails as well. So thank you again. Looking forward, very glad again to be back with you folks on a more regular schedule, and I will see you in a short while. Bye, everybody.